Hello, everyone. Welcome to this week's Scrum seminar. We have two talks today. Our first talks are given by Tobias, Heinrich, Nagel, who is a PhD student from Fraunhofer Institute for Manufacturing Engineering and Automation. Tobias' research mainly focuses on the identification of dynamic systems with artificial intelligence. So without further ado, welcome, Tobias, and you may want to start the presentation.
Yeah, thank you so much. Okay, so yeah, as already said and told, I would like to give a talk about the so-called Kalman-Bucy-Informed neural network. Let me just switch on my laser pointer. No, here we go. For system identification. So this is basically a talk I already gave on the conference on decision and control. This is a quite big control conference. It took place in last December in Cancun. And what we wanted to do here is we wanted to combine physics-informed neural networks for actually identifying system parameters. Well, first of all, where do I come from? I'm working here at the Fraunhofer Institute in Stuttgart, which is located in southern Germany. Oh, wait, Zoom wants to do script. Do you also see this here? Maybe I can switch this off. Here we go. This is better. No. I think it was only visible for me. It was a Zoom message. So now it's better. Yes, here. This is the Fraunhofer Institute in Stuttgart. We are located in the southwest of Germany, so in the heart of Europe, basically. The Fraunhofer Institute is quite close to the University of Stuttgart. This is located in this building here in the back. And me, myself, I'm sitting here in this building. Of course, right now it's deep at night. We have 6 p.m. right now in Stuttgart. Yeah, and the Fraunhofer Institute for Manufacturing Engineering and Automation, we basically do everything in the manufacturing engineering. So we have a big robotics department. We have a department for artificial intelligence, but also for signal processing and so on and so forth. So we were quite a large institute with roughly 1,000 roughly 1,000 colleagues, and yeah, I've been working here for 4 years now. This is a short agenda, what I wanted to talk about in the next, I don't know, like 40-45 minutes. We will see how long I will need. First of all, we'll go into a motivation and problem statement. So basically what motivated us to do all this whole paper. I will talk about some preliminaries. Then I will introduce the Kalman-Bucy-Informed neural network. I will present some experiments we conducted. The experiments are, for now, mainly focused on simulations. And finally, I will do a short summary and take a look at the future work we're not only planning to do, but we're actually in the middle of work. So motivation. We already heard that I'm kind of working in the control engineering area. Control engineering is basically that you have any dynamic system and you want to control the system into a desired state. For example, we have here in pendulum. This could be an inverse. This could be a standard pendulum with a motor here, and we wanted to switch this pendulum in the upward position, but we do not really know what input U is necessary for that. And what every control engineer roughly does is he wants to build a mathematical model which describes the system precisely. And afterwards, when he has this mathematical model, he wants to build a controller so we can reach a target state. And this first step here is usually really difficult. I mean, of course, for a simple pendulum, it's not that difficult. But even if we have, for example, a double pendulum, if you look at the equation that describes a double pendulum, we have we need actually a lot of time, and this is also what most students hassle with. And yeah, this is why in my research I basically focus on this first part here, where we build a mathematical model that describes the system precisely. Usually, especially in dynamic systems, these mathematical models are basically differential equations, because in nature, with these differential equations, you can often describe something quite precisely. In our case, we mainly focus on so-called nonlinear ordinary differential equations. So no partial differential equations. These are for now enough. And what you can see on this slide is my first approach. I wanted to see whether I can set up a differential equation ODE based on the measurements. So I have some measurements of my system, and I want to see whether I could find any differential equation that fits to these measurements without actually needing to calculate the dependencies inside the system. And what you can see here is my first approach, which I started at, I think, 1.5 or 2 years ago. And I thought, okay, how does this ODE look like? So basically, we have 3 parts. We have the first part, the appearance of the ODE, the arrangements of the summands, for example, which operators we have in general. And I thought, this is I could just use this as a hyperparameter and do not focus on that too much. I wanted to focus basically on 2 points. Firstly, on the operators. So which operator here is correct? Do we have a sine here, or cosine, or a squared operator? And this is basically nothing else but a classification problem. My first approach was that I could do this by reinforcement learning. So I would have some measurements here. I would feed these into a reinforcement learning algorithm, and stepwise, the reinforcement learning algorithm should basically tell me which operator fits here to these to these measurements. The thing is, we also have in every system, we also have these coefficients. The coefficients describe basically some settings inside the differential equation. For example, in a pendulum, we have masses and lengths, and these are expressed by these coefficients. And they are basically a regression problem because they are continuous. They are not discrete. And the thought was that I could just let the reinforcement learning algorithm do the classification part, and afterwards feed it into an optimization algorithm where I could use where I could only find the coefficients here. And ideally now the found ODE should be as close as possible to the original one. This was the dream. What was quite curious, or what was quite surprising for me, is that this first part was not that difficult. Actually, the second part was really difficult. So the reinforcement learning algorithm quickly could actually find some fitting of operators here. But this regression problem here was really hard, at least with simple optimization algorithms. And this is why this is how we actually came to this topic here. So and this is basically what this whole method is about. So we want to find parameters in an ordinary differential equation. So I already introduced a simple pendulum, which is quite easy. In our case, or for example, in the paper, I try to identify the system parameters of a double pendulum. Double pendulum is well known, I think. We have a simple pendulum with a length L1 and a mass M2, and appended to this is another pendulum with the length L2 and the mass M2. So this system is quite chaotic, and we have some weird oscillations inside here if we deviate it from its initial point. And what we assume here is that we can measure the angles phi1 and phi2, and in this case also the angular velocities phi1 and phi1 dot and phi2 dot. But we can only measure them with some Gaussian noise. So we can only measure them after we added some Gaussian noise on that. We also assume that we know the governing ordinary differential equations. And these equations are quite long because if you take a look inside here, we have these second derivatives which again appear here and here. So we need to set them in, and if you do that, it would be over the whole page. So we have a quite complicated ODE. And what we wanted to find out is whether we can calculate the masses and the lengths of the pendulum suppose we only have the measurements of these angular velocities and the angles. This slide sets up this problem in a more formal way, and also in a way that usually control engineers would tackle this. So what we have basically is we have a state space representation of a continuous time, nonlinear, dynamic, and time variant system of rank n. So n for a double pendulum would be, for example, 4, because we have a state space rank of 4. And this is defined by means of this differential equation. We have x, which is the state. X dot is the derivative of the state with respect to time. F is our nonlinear ordinary differential equation, and it transforms our state x, some system input u, so we could move the pendulum, some process noise w. The process noise is usually used to describe some model uncertainties, the time t, and also a parameter vector theta. So theta is a thing we're actually searching for. Usually our state vector is not directly accessible. It's in its most general way. It's transformed non-linearly by this function g. By this nonlinear function g. And again, the state vector x and the input u, but this time we have some measurement noise v here at the time t. So what is our target now? We want to acquire some noisy measurements. Those are denoted by this overlined y here at several discrete time steps. And what we want to do is we want to find the parameter vector that minimizes the difference between the expected outcome y and these measurements. And if we take a look up again, we can see that the theta is kind of hidden here behind this differential equation. Usually with the most straightforward approach, so with a simple optimization algorithm, we'd need to solve this differential equation here, at least numerically. And this is actually a big issue for many differential equations. Why would that be? So as I said, the most simple approach would be the usage of simple optimization algorithms. We just use a standard gradient descent algorithm. We need to solve the ODE numerically in each and every optimization step, and then we go into the next step. The thing is, many ODEs cannot be solved analytically, so numerical solutions are often our only way to go, or in general. But numerical solutions also have their drawbacks. I wrote here the most basic numerical solution to an ODE, which is basically the Euler method. I mean, there are better ones which are more precise, but this is the absolute basic one that describes how we can solve an ODE numerically. And what we do is basically we discretize the ODE and we say, okay, the next state is always the last step plus some time difference times the derivative at this point. And what we do this way is we approach the black one is the true curve, and we approach this true curve discretely with every time step. But the thing is, on the one hand side, if we go further in time, our error might get larger because our next prediction is already based on the last prediction. And on the other side, if we need to choose a really small delta t here, so we're actually correct here. So the smaller our delta t, the more correct we actually are for this method. And this is basically the biggest problem here, this delta t, because if our system is stiff or oscillating, so stiff means that if we have some edges here on the black curve, for example, or if we have a highly oscillating behavior, we need to use a really small delta t. And you can imagine that if we need to solve this ODE numerically in every single optimization step, because we still want to find the parameter vector theta, then we'd have we'd have to use a lot of computing power on the one hand side. On the other side, there could also be the problem that if we actually if in our optimization algorithm we'd run into a theta that depicts an unstable behavior, our solution would shoot right into the air, and our algorithm will also fail. So this is also something that I observed. And basically, this approach, which is used quite often in the literature, was a huge issue for me. Yeah. So what is the rest of the state of the art? So what could we do if we look up a little bit into the literature? The first approach could be a subspace-based state-space estimation. Subspace is kind of a tongue breaker. The subspace-based state-space estimations is a concept which is quite frequently used in the control engineering area, where we have a linear state space model and we want to fit some measurements on this linear state space model. And we could, for example, use some regularized least squares algorithm for that. There are also other algorithms. I found this one the most convenient, and it works really, really well. I tried it out on several data settings, but it works really well mainly for a linear system. So for basically non-linear system, we cannot really apply this every time. The second approach would be the one that I already talked about. We could use standard optimization algorithms like an LBFTSB algorithm or a particle swarm optimization where we solve the ODE numerically in every time step. But the thing is, for example, those gradient-based algorithms, for every single gradient, for every single optimization step, we also, when we want to calculate the gradient, we again need to solve the ODE numerically in every direction for the parameter. And also this leads to a huge computational effort. So basically what I already talked about, this often works. This often works for many ODEs, but not for every ODE. And there are a lot of ODEs where this could fail. And if you remember my first motivation slide with the reinforcement learning algorithm, if I at some point stumble across an ODE that is quite hard to solve, this method actually failed. The third approach would be machine learning techniques. And so basically, we tried out heavily the second approach, and we kind of had our difficulties with that. And the third approach was basically then the machine learning techniques, because afterwards we thought, could there be maybe a better way of actually finding those parameters? And there we stumbled across these physics-informed machine learning techniques, where we have not any heavy focus on noisy data yet, and which is why we thought we could leverage this approach here. So physics-informed neural networks is something I'd like to talk about in preliminaries. And this slide basically describes what is a so-called physics-informed neural network. So these physics-informed neural networks, or PINs in short, they have been described by Mr. Raisi and by Mr. Pellikaris and Kandidiakis, and basically already in 2017. There have also been papers which suggested this method even beforehand, but I think this paper from Raisi is the first one that actually made them quite popular. So they're used quite frequently. And this physics-informed neural network is nothing else but an absolutely standard neural network. So we do not necessarily need a CNN. We do not necessarily need a residual neural network or some fancy stuff. The only thing we need is a simple, straight feed-forward network, a fully connected network. And what we want to do with this network is we want to approximate a viable solution to the given ordinary differential equation. Well, how could we do this? We take this standard neural network with only, for example, here two input neurons, one for the time t, another for the input u. And the output now should be the state of our ODE. And if we do not train our neural network, this output would be absolutely random. So how can we train this network that the output x here is actually a solution to the ODE? And this is quite simple. On the one hand side, we can calculate the derivative of this output, because neural networks have an interesting behavior. They are actually fully continuously differentiable if we choose an activation function that is fully differentiable. So for example, if we choose a hyperbolic tangent function for the activation here, then we can, for all the activations inside this neural network here, then we can actually calculate the derivative of this output with respect to this input t here. And this is what we're doing right here. So we can calculate the derivative with respect to time here. On the other side, we know our ODE. This means we could just feed in this output into our already known ODE, and ideally also here, if we chose the correct state, then also the derivative should be calculated here. And now this whole network becomes trained by simply minimizing the difference between these two derivatives. I actually saw a lot of papers where people mostly trained on the derivatives, maybe on one single initial point and afterwards only derivatives. And I wanted to try that by myself to find some viable solutions to the ODE, but I had a really hard time to training only on the derivative. On the other side, as you can see here, we do not have any parameter vector theta yet included. So we are not using that yet. So as I said, for me, just approximating solution without any further ado was quite hard. But identifying parameters worked really well. And the question is, how could we now use this to identify parameters? Well, it's quite simple. We feed in a parallel, we feed the state x into our output equation, and then we actually gather the expected output y. And what we do now is we minimize the difference between this expected output on the one hand side and the measurements we took with some parameters, and we minimize this difference and train this as well. And what this is it keeps the state x transformed by g close to our measurements on the one hand side. On the other side, this left part tells us that our x should be a viable solution to the ODE. And these two combined means this can only be possible if we choose the correct parameter vector theta, which is also a tunable value, which becomes trained in parallel to the neural network weights here. So parameter vector theta and the neural network weights become both trained on these two terms right down here. I already told you that it was quite easy to actually find some parameters, and this is what I wanted to show you here is a comparison of a parameter identification. What you see here is the Fitzhugh-Nagamore system. I read that this and this is the differential equation of the system, and it's basically what you do here is you can model some voltage spikes in a neuron after simulating it by an external input current. So it's used kind of in the biology field. And if you solve this ODE numerically for some initial points, then you get this red and this blue curve for x1 and x2. Here, for example, with these target parameters. So we have 3 parameters, alpha, beta, and gamma, which are right here, gamma, alpha, and beta. And if they're chosen this way, then we get this curve. And what we wanted to do now is we wanted to see whether we could find alpha, beta, and gamma again by using here an LBFGSB algorithm or a differential evolution algorithm. And afterwards, with the found parameters, I did a plot. I again tried to simulate with the found parameters the curve. And as you can see here with a dashed line, these are the predictions. They are quite there's quite a big difference compared to the original curve, which is safe to say that our algorithms actually failed here. On the other side, the pin approach, maybe you could do this a little bit bigger. Yeah, here we go. On the other side, the pin approach, you can see here, those are actually quite a lot of curves behind that. They're all really close. So this means that the parameter vector we actually found depicts in very similar behavior to the original curves here. And this means that our pin approach was able to find the correct parameters. And this is why I think this physics-informed neural networks are so strong.
Sorry, Tobias.
Yeah.
May I ask a question?
Yeah, Claire.
Yeah, on this slide, so I see on the pin approach result for the pin approach.
Yeah.
What is the difference between X1 predict and X1 NN?
I see. Sorry. So basically, I had those three curves here. X1 and X2, of course, are the original data. X1 predict and X2 predict are the predictions with the found parameters. The curves, and X1 and N and X2 and N are the output of the trained neural networks. So the trained neural network output is the third curve here.
So the predictions are obtained by solving the ODEs with the learned parameter, right?
Yes.
Okay,
correct.
got it. Thank you.
Okay. So, but the thing is, what you cannot see here is any noise. So I have not included any noise in this data. And if you include any noise, then you'd also have some more difficulties with the physics-informed neural network. And this is why I thought adding some noise to the system would be quite beneficial. And the way I did add some noise was with a so-called Kalman filter. So Kalman filters are quite popular in the engineering field. I'd shortly introduce them here. And the original Kalman filter that people usually learn in university are based for a discrete time linear state space model. So this is basically the same thing we already saw, but only this time it's only discrete time and linear. And the thought of a Kalman filter is now that we could extend this model with some noise. So we add here a process noise W or a measurement noise V. And what Mr. Kalman now thought about is, hey, why don't we define xk now as a random variable? Because if you added some noise here, it would be much more precise to propagate the state through time by defining it as a random variable. The thing is, how do you propagate a random variable through time with this equation? So if you have a normal distribution, a Gaussian distribution, then the mean value and the covariance matrix are basically enough to describe it completely. And this is why Mr. Kalman came up with a so-called Kalman filter, which allows us to propagate the random variable of the state through time. It does so by basically alternatingly perform a prediction and a filter step. And the upper two equations are the prediction step and the lower two equations are the filtering step. They are actually quite easy. In the prediction step, we have basically our model from up here. So we want to predict which value will come most likely next for the mean value as well as for the covariance matrix. And in the filtering step, we afterwards try to compare this, our last prediction, and see whether our prediction fits actually some measurements we conducted, weighted by this Kalman gain K. And now if our variance is a little bit higher, then the measurement becomes weighted a little bit more, and if it's less, then our prediction becomes weighted a little bit more. And this is how it we can actually propagate this random variable through time. But the problem about this is, as I said, okay, we are still in a discrete time linear state space model. We actually want to have this for a continuous time and non-linear case. Luckily, there's a so-called extended Kalman-Bucy filter, which is everything we're actually, everything we were actually hoping for. We again have our nonlinear dynamic system that we already introduced with some process noise W, some measurement noise V, and an initial value X. And the extended Kalman-Bucy filter is now defined by differential equations because we are now in a continuous time case. For the extended Kalman-Bucy filter, it is possible to actually combine the prediction and the filtering step into one single equation, and this means that our mean value here is basically nothing else but the ODE that describes our mean value is basically nothing else but our classic differential equation without any noise here, plus a weighted difference between the measurement y and the expected outcome g, weighted by this Kalman gain k. On the other side, the covariance matrix P here is basically a matrix Riccati equation. I don't want you to learn these two equations by heart. I just want to let you focus on the fact that we do need to perform some linearizations here around the single states. So a hat, for example, is the linearization of f with respect to x. And this means that usually calculating this is a huge computational effort, because for every single time step, you'd need to perform all these linearizations, build all these big Jacobi matrices. And as I said, when I once learned about this extended Kalman-Bucy filter in university, I remember that my professor told us that basically nobody uses this extended Kalman-Bucy filter because it's computationally so heavy. But with the automatic differentiation, which we can use in, for example, TensorFlow or PyTorch, those operations are not that computational heavy anymore. So we can do this quite efficiently. And this is what we are basically doing for the Kalman-Bucy-informed neural network. So,
hey,
yep.
May I ask a question?
Of course, yes.
So for the Kalman filter, you have the model and the measurements, right? And in this case, are you using synthetic data? Is it like the data that you generate to create all the experiments?
What you mean for this overlined Y here?
So what differs the measurements from the model? Like,
yes,
you have the two components.
Yeah, so usually the measurements are some noisy measurements with some wrong which you basically acquire by measuring. In our case, we did not have a double pendulum available, which is why we simulated it and afterwards added some noise on this, but also we falsified our differential equation. I will come back to that later. So we would actually be as close as possible to reality. Yes, of course. This overland Y here is the measurement. This is the expected outcome. And if we'd have a perfect model without any noise, then this would be 0. Yes. But usually we do not have a perfect model. Yeah. Sorry, Ian?
Great. That's much clearer. So just one follow-up question on that. So if the deviation is in terms of noise, how, maybe you'll show it later, if so then I'll wait, but how is it like you could use Kalman filter for like the noise in order to get the more accurate results, but you could also just clean the noise in like beforehand and just use the model, right?
Yeah, you mean I could remove the noise by, I don't know, for example, using a mean value, so meaning it out, or
some filter, a bandpass filter, some smoothing filter, some I forgot the name. There's the way to remove Gaussian noise.
Yeah, I mean there are certainly
filter.
There are certainly other options, and basically this is kind of the same what an extended Kalman-Bucy filter does, because it's basically a minimum variance estimator. So it tries to minimize the variance by fitting the mean value into our measurement, but also keeping the variance as low as possible. So this is basically what a Kalman filter does.
All right, cool. Okay,
it's quite similar, but I will come back to that later actually, and then we can see some advantages we have here.
Perfect, thank you. Looking forward.
Just remind me if I forget anything. Just feel free to interrupt me. This is no problem at all.
Right, thanks.
Okay, so what we have here is now our Kalman-Bucy-Informed neural network. Let me go back to this slide again. And so what we can see here is that we basically have 2 differential equations. And this is basically what we're using to create our physics-informed neural network. So in the physics-informed neural network, we had 1 differential equation that we try to solve implicitly. And what we do now is we create 2 neural networks, 2 physics-informed neural networks, which try to adapt these Kalman-Bucy filter equations. And this is what we're doing in the Kalman-Bucy-informed neural network. So the general idea is easy. You can see it here on the right hand side, the sketch of the method. We have basically 2 neural networks: one for the mean value, which is called the Xi network in my paper, and one for the covariance matrix, which is called the Psi network. And What we want to do now is we want to adapt these two differential equations I just showed you. And we do basically the absolutely same thing that we saw in the physics-informed neural networks. What we have here, again, is we propagate the time and the input u to acquire is a mean value x. And we calculate the derivative of x with respect to time, t. So we can, again, calculate the derivative of this neural network and acquire then this x hat dot on the one hand side. On the other side, we can just feed x into the first ordinary differential equation, which was described by the Kalman-Bucy filter. In this first equation, there's not only there's not only the mean value necessary, but also the covariance matrix and the theta here implicitly via the measurements. So basically, all of these three elements are fed into this first equation right here. As I said, the covariance matrix is kind of hidden here behind this Kalman gain, so you cannot see it directly now. And what you do now is we again train here only on the derivative and try to minimize all these three parts here. For the covariance matrix, we basically do the absolutely same thing. We again calculate the derivative with respect to time and acquire the derivative of the covariance matrix on the one hand side. On the other side, we feed this into the second equation, which was the matrix-Riccati equation, and which required us to do all those linearizations. But all of this can be done quite efficiently in TensorFlow or PyTorch. Now, we already included everything here. And so it basically, in theory, it should work right now. But in experience, I tried this out and I had some issues here with training only on these derivatives. As I already said, training only on the derivatives is sometimes really unstable. And this was quite a big issue for me, although we already included the difference between measurement and expected outcome, but only in the derivative. So I thought, okay, maybe we can force this mean value x to be as close as possible to the measurements on the one hand side, and on the other side, if we are not close to the measurements, it should be at a maximum of a covariance matrix value away from the measurement. So if we are a little bit more away from the measurement, the covariance matrix should be a little bit higher at this point, and if our mean value x is close to the measurements, then the covariance matrix should be a little bit lower. We do not do this here yet, but we do this now. If we feed the mean value x and the covariance matrix p through our output equation, then we can calculate a mean value and a variance. And this mean value and variance become now trained and combined with the measurements by a simple maximum likelihood estimator. So the maximum likelihood estimator tells us what is the most likely distribution. So what are the most likely values for the mean value and the variance, so it fits actually to this measurement. And this third part really keeps the mean value close to the measurement on the one side, and the covariance matrix also in correct numbers. Yeah. And basically, this is a general idea of the Kalman-Bucy-Informed neural network and how we can find our parameter vector theta, because if now this becomes trained all in all, it is only possible that the correct parameter vector theta is found. And we can show this in some experiments. So in the experiments, we took a look at a double pendulum system as well as an elastic pendulum. And for example, here for the double pendulum system, I already introduced it. We compared it to the MATLAB implementation nonlinear gray box estimate. And it can be described by a state vector x and this corresponding ordinary differential equation. I shorted it a little bit down with these C1, C2, C12 or S12 for the sine and cosine. And what we have is basically we have the lengths L1 and L2 of the pendulums, as well as the masses M1 and M2, but the masses are kind of hidden behind this quotient here. So we can only identify this capital M here. Another thing is that we actually, what is quite interesting is that we could falsify our differential equation because we include some process noise, which allows us to falsify it. And what we now did is we simulated some data from this equation with these damping terms here. But for the Kalman-Bucy-Informed neural network, we only use the black part, so without the red part here. And looked whether we could still find our correct parameters. And yeah, as you can see here, this worked actually quite well. What we did here is we performed on the left side, on the left plot, we performed 10 identification runs to identify these lengths L1, L2, and M. We chose them to be between 0 and 1. And for each time we varied the initial values x0, and we added new noise to prove that it was not some random coincidence. And this led to the left result here. In blue, we have the K-bin estimate. So this is the absolute error. The absolute error between the original parameter and the found parameter. In blue for the K-bin, and in red for the MATLAB method. And you can see that we're usually here in the area of 10 to the power of -2. Maybe sometimes we even scratch 10 to the power of -3. And this means that we are quite close to the original values. On the other side, when we submitted the paper, one of the reviewers asked us whether our method is actually whether our method actually also works if we lower our sampling frequency. So he basically asked if we have some measurements, how tightly do these measurements have to be time step wise next to each other? Because obviously, since we are performing some linearizations, the less time steps, the less data we have, the worse our results should be. And this was actually the case here. Besides those outliers here, you can actually see a declining number of a decline in the absolute error. If we have only a sampling frequency of 3 Hertz, we are not better than the MATLAB method. But as soon as we're going down here, we actually usually are better. Keep in mind though that these single values are only based on 5 parameter identifications here per run. This is why they are a little bit fuzzy. The reason for that is that one single parameter identification needs a couple of hours, and it took too long to actually perform a lot of experiments here for every single sample frequency. But all in all, the lower we are, the higher our sampling frequency is, the better our error is. What I show here, what you can see here is also some plots we performed. So we thought, okay, we found some parameters, but do they depict the same behavior as our original measurement? And here the solid line is a single randomly taken out parameter, which we simulated here, and the dashed line is the parameter with the K-bin found. It's a simulation with the K-bin found parameters this way. On the dotted line, we have the MATLAB identification, and you can see that our identification actually depicts a similar behavior as the original one here for the angles as well as for the angular velocities. Down here, you can see the output of our Kalman-Bucy-Informed neural network, so actually of the neural networks that we had. And you can see that the mean values actually fit inside the measurements quite well, and the covariance matrix is also estimated here quite correctly. As you could see in the last slide, we had actually some outliers here. So these happened from time to time, and also in this this plot right here. And we did keep them in because we thought, okay, this is sadly a part of the method. Sometimes we expect or we assume that our Kalman-Bucy-Informed neural networks becomes stuck inside a local minimum. And if we restart our algorithm, then the solution becomes better again, and we actually find a viable solution. But being stuck in a local minimum happens from time to time, and this is one of the drawbacks of our method. But luckily, if we are stuck in an outlier, then our method tells us this, because if we are stuck, then the Kalman-Bucy-Informed neural networks depict a really, really bad behavior right here. And the mean value and covariance matrices are not estimated correctly anymore, or I mean, they are estimated correctly, but the covariance, the variance is estimated really, really high in this. So this behavior indicates that our algorithm actually failed, and we could see this without actually testing whether our parameter is correct or not. We can already see this in the training procedure. But as I said, when we restarted the algorithm with a new neural network weights, everything worked fine. We also performed another experiment, regarding an elastic pendulum system, and this elastic pendulum is also quite chaotic system. We have this differential equation, which is shown here on the left side. We have a couple of parameters, spring constant, mass, the initial length of the pendulum, as well as we also wanted to predict the gravitational constant G, which is of course known, but we wanted to do that just to check whether our method is successful. And again, we added some damping terms and damping coefficients here behind. And again, we used this whole equation with the red part to simulate data and remove the red part for our Kalman-Bucy-Informed neural network. And here on the next slide, you can see the results for this elastic pendulum system. On this left plot, you do not see the error anymore, but you see for a single parameter setting how close we were to the parameter. The reason for that is that I wanted to show that we had actually also some difficulties if our parameters depict if our parameters are really far away from each other. So the gravitational constant G is 9.81, so like 10 times, roughly 10 times the value of the other constants here. And also this led to an often successful identification, but we had some more outliers here if our parameters are really far away from each other. On the other side, in this elastic pendulum system, we also wanted to make it a little bit more difficult. And what we did is we did not assume that every of our state was actually measurable. So we only assumed that the angle and the deviation of the spring were measurable, but no velocity at all. And what was really, really cool is that our Kalman-Bucy-Informed neural network implicitly fitted these velocity values, as you can see here. The black line is the true value which we did not feed to the Kalman-Bucy-Informed neural network, and the green line here is the estimated area where our Kalman-Bucy-Informed neural network expected it to be. Yeah, what you could also sometimes experience is that in the last couple of measurements we had some bad fits here. This is because for 8.1 seconds, for example, we do not have any data anymore. So this becomes punished less heavily than in the false prediction here in the beginning, but this did not lead to a wrong parameter identification at all. So I'm almost finished. So it's like 10 minutes left, and I would like to do a short summary of the work. So in summary, actually, our proposed method actually allowed us to identify parameters with noisy measurements. We could even include some small errors in our model, and we also observed that our model scales really well with an increasing parameter count. Since besides the parameters, we already trained 2 big neural networks. Yeah, and the thing is, our method has some drawbacks. I think the biggest one I haven't talked about yet is that our method success relies heavily on the correct architecture of the neural network. So the thing is, the only possibility to find the correct architecture is basically by trial and error or by using a neural architecture search. But you can sooner or later you will find a fitting neural network to find the parameters. Also, what I already talked about is sometimes we do reach a wrong estimate, which is likely that our backpropagation algorithm is stuck in a local minimum. Also, of course, our training time is rather high, so we need on a graphics card server, we need like 1 hour or sometimes 2 hours to actually find correct parameters here. For future work, we already identifying the ODEs as a whole, so not only parameters, but the whole differential equation. Sadly, I couldn't talk about that because it's not published yet, but I think the results are really, really promising and they're quite cool. And what we are also working on is that we want to use this method for a real-world case for an electrolyzer. So an electrolyzer is basically a device that generates hydrogen and oxygen from water. And here on the right side, we can see an equivalence circuit, which I took from this paper here from Ursula and Sanchez from 2012. And what you can see here is basically, again, an ordinary differential equation. But in electrolyzers, you have the difficulty that your measurements are usually not performed time-wise, but in the frequency spectrum. And this changes a lot. And we want to think about how we can use our method actually with these real-world data, which is not which is in the frequency spectrum. Yeah, so I almost needed 1 hour now. Thank you so much for listening. If you have any more questions, feel free to ask them to me, or you can also send me an email. My email address is written right here, tobias.nagel@ipa.fraunhofer.de. Yeah, thank you so much for listening.
Thank you, Tobias, for your wonderful presentation. I see a question on the chat. So basically, he wants to ask, is there any publication associated with this talk so
Yes.
we can refer to?
Yes, of course. The publication is on arXiv. So if I don't know how I could give that to you. I mean, if you just Google this name here,
okay,
you directly find it on arXiv. Since the CDC was only in December, I don't think that there's already a publication on IEEE, sadly, because usually they need like half a year.
Sure, no problem. Let me find it on. Oh, I see this. So I'll put the link in the chat. All right. Are there any questions for our speakers? Right. Thank you again for your presentation, and thank you for sharing research with us. And now we move to our second talk. Our second talk is given by Omer San, who is from Oklahoma State University. Omer is a associate professor of mechanical and aerospace engineering, and he teaches graduate, undergraduate courses in data simulation, computational methods, and fluid dynamics. He received his PhD in engineering mechanics from Virginia Tech, and he is a recipient of the DOE 2018 Early Career Research Program Award in Applied Math to develop scientific machine learning algorithm for multi-scale closure modeling of geophysical turbulent flows. So, hi, Omer. Hi, Professor.
Hi, Omer. How are you?
Good. How are you?
Good, good. Thank you. Thanks for inviting me for today.
No problem. So you try sharing.
Okay, let me try.
Sure.
Okay. Do you see?
Yes.
Okay. How about now?
Yes.
Okay, perfect.
Great.
And are we starting now or
yeah, sure.
Okay. Yeah. So thank you very much for hosting me here today. So I would like to talk about today like a generic framework rather than a specific a specific idea. So I wanted to kind of illustrate like what is the role of inductive bias like in scientific machine learning, in physics data, like hybridization of physics and data modeling framework. So and before I move on, so I really would like to thank like several individuals here, in particular, like I mean my recent PhD students like Romit, Suraj, and Shadi. So they have been instrumental on developing like this hybrid modeling and analysis framework within Oklahoma State University. So I mean, where we came up with this story, like I think we started like to think like how we combine like two different disciplines, like I mean a physics-based model, like I mean I'm coming from a turbulence modeling background, like large simulations or direct numerical like modeling, I mean direct numerical simulations, so PDE-based like simulations. So I mean there are like lots of issues in those models, like there are, I mean, we have like certain physics, we approximate, there are like errors due to the numerics, there are errors due to the like turbulence models and many other components. So, and on the other hand, like, I mean, I think in 2015, 16, we kind of realized that like there are like powerful machine learning, like especially in neural network tools available. So then we started to think how we can synergize like these two disciplines, these two kind of different modeling paradigm. And then the way I kind of formulated like all group is a interface modeling. So there is an interface between the physics-based solvers or physics-based ideas or concepts or conjectures, and then data-driven like approaches. And then my kind of approach over the past few years is to kind of synthesize like the best out of these two paradigms. So, and then we are not the only group. Like, I mean, there are lots of, I mean, ideas, like great ideas have been already proposed, promoted like in the literature. So, I mean, Misha Chertkov from University of Arizona is calling physics-informed machine learning. Like Professor Karniadek is called like physics-informed neural network. Like, I mean, and then physics-based machine learning, hybrid alloys. So, I mean, they're all different. Like, I mean, the components or the approach in each different paper, each different ideas are slightly different, but we can classify them like these are a kind of procedure or process to exploit the powers of like this paradigm, like physics and data science. So, and then it becomes like scientific machine learning in the literature. So physics for like machine learning for physics. So then without kind of further like introduce like what I mean by in our group, so inductive bias approaches or inductive the role of the inductive bias in this scientific machine learning area, I wanted to give a very simple example in the beginning, just to illustrate like I mean how I think and why I think that like what our method is a bit differentiated from let's say PIN method, like physics informed neural network. So to illustrate that one, so I'm considering, let's say, a simple ordinary differential. I mean, this is just a cook-up example. Like there is no physical meaning at all behind this example. It is just an ODE, and then like I put it here like an ODE, and then we know the true solution of that ODE. It is kind of a composite function of like the fourth power of function and a harmonic function. And like we can collect 32 sample points in our true data, let's say like true solution, and then we can train a machine learning like neural network, a simple plain vanilla like feed-forward neural network, and then we can look at the prediction, like when we can test, I mean, how we learn. So I mean, this orange bar here, it is the standard deviation of a trained like 10, 20 different like neural networks. So the standard deviation I put like as an orange bar here. Okay. So as we see that, like, I mean, we get the trend like from a plain vanilla, like, I mean, arbitrary neural network. I mean, but yeah, what we can do better. So then the PIN comes into the picture. Okay. So I mean, if we know the equation, like the governing equation, so we can kind of add this information as a regularizer to loss function, and then we can see what we have. Okay, the previous picture, in this picture, I used 32 sample points to train the neural network. Okay, so in this picture, I'm not using 32 train point. Okay, so I'm just using the equation. Okay, so as we see, like, I mean, I'm not using this 32 grid point, like I'm not grid point, but the collocation point, the true value, but I'm just using the equation just to see, like, can I get some sort of like, can I learn something like by using like the PIN? So, I mean, because like we train, like, I mean, the differentiation, like the differential form, so we can get the differential operator, like the differential, I mean, the first order derivative correctly in upper corner figure, but the actual value is off. So, and then what we have usually in ordinary differential equation, we have initial conditions. So we can provide initial condition data while we are training, so we can force like the algorithm to the point, like to the point. So when we force it to the point, but I am still not giving the true data. So I'm giving the equation, the true equation, plus the initial condition in my training. So it is still not able to provide a accurate inference, like accurate prediction, because of like there is no, I mean, like true solution involved in the process. So then we started to think like, I mean, what we can or how we can kind of. So we can.
Professor, sorry to interrupt. Can I ask a question?
Sure, anytime.
So I see in a lot of figures you show here has they have the min max. How do you obtain those min max? So
like, I mean, the, you know, like, I mean, we can train like 10 or 20 different neural networks, like, I mean, different, I mean, like you can stop in different place, you can change like number of neurons or whatever. So, I mean, we train like 20 different model, 20 different neural networks, and then I use the like the bounds of the, I mean, one of them is this, and then the minimum, and then the maximum. So, I mean, this band is the model output, the minimum and maximum of the model outputs.
Yes. So the dashed line is the mean, right?
The dashed line is the average of these 10, 20 different like neural networks, the average of all the neural networks. The minimum and maximum is like the worst, and I mean the one of them and the other one, like the upper model, like just one model, and then the other one is another model, and then all these 10 or 20 different neural networks. I mean, I'm saying 10 or 20 because I don't really remember like how many neural networks we trained here. Like it was some number of neural networks. I mean, it was like quite a bit ago. Like I really forget. Like we use like 10 ensemble or 20 ensemble. Like I forget the number, but like some number of neural network, and then this bandwidth is the. I mean, just to show that like any of these neural networks, the trained neural network is going to be in between this bandwidth. Like,
sure.
I mean, that's just the kind of the bandwidth of all these predictions. So I mean, if I plot like, I mean, 10 or 20 different predictions of the neural network, it is going to be inside of this orange bar. Okay, that's what it is. Okay.
Sure. Thank you.
And then here, like we can weight them. Like I can kind of like say that, okay, I am trusting my equation 100 times more than the initial. So I can weight like between in my loss function, I can scale them up. Okay, like I mean I can use 100 or 1,000, whatever, like I mean, but I can scale. So if we scale, like I mean, without scaling, like that's the result. If I scale, I can get a better. So I can tune up like these numbers. Like I can scale 100, I can get even better, so on and so forth. So I mean, there is always a kind of a way of like optimizing all these parameters. So we can, like, if we work on like as a kind of like I mean, if you make another outer loop and optimize the neural network parameter, we can even get a better result. So I mean, I'm not particularly selecting a worst or best case scenario. This is just arbitrary. Like, I mean, I arbitrarily choose 100 here as a weighting function without any intention. I just wanted to illustrate that like there is a way of making better or worse, like I mean, by weighting like this thing. So, but my point will be clear in a minute. Like I mean, so these ideas like came. Okay, so still we need like some sort of like data points to make it better. So what we do? So assume that like I have the equation itself, like I know the equation itself, plus instead of just initial condition, assume that like within my bounds, like this x, like the domain, like from 0.6 to 2.4, I can sample 32 points. Like, and then I feed like these true data points in my loss function, like I mean just 32 points. So then the pin, like I mean the physics informed neural network, gives like probably the best results so far. I mean the methods that we, because like I mean it respects the equation itself, and it also has the data. So just for comparison, so this is the in the small corner, like this is the regular machine learning, the standard like feed-forward machine learning just trained by 32 points, same neural network architecture, same number of neurons, same number of layers, and same number, same activation. Everything is same, not similar, same, but just, I mean, the regular loss function, I mean, just the 32 points like loss function coming from the 32, and then the other one is we also provide the equation itself. So there is a significant improvement because of this PIN idea, like this physics informed neural network, because we kind of bound, like, I mean, we regularize the training by Professor Karniadakis, like PIN idea. So which is great, good, but there are issues, like, I mean, like in, let's say, in different scopes of modeling and simulation. So like we may not have the equation, the full form of equation, like the complete or algebraic form of the equation or governing equation available. Okay, so let's, for example, to illustrate some thought experiments, like some thinking experiment, assume that like we only know the part of the physics. So the original physics, like the original equation has more term. So I just filter like two sinusoidal term from my original, assume that like I don't have that information, but I only have this two term, like y prime minus 4, like x minus 1 cube equals 0. Okay, it is a partial information. So, but the true data comes from all these like oscillatory kind of behavior. So, and then if I train, I mean, my physics informed neural network by constraining like this missing information, okay, and then it does, like, I mean, it only captures this, like this exponential, I mean, the polynomial term. So it is not, I mean, even if we have the true data, so it is not able to, it's not able to capture, which is normal, expected. So I mean, this is where like PIN might not be like the case to go. Like, I mean, if we don't have the full information, because like if we don't have the full information, if we constrain, if we regularize with missing information to our system, like we can even deteriorate like the solution. That's one way to think. Like, I mean, the challenge to PIN idea. So, and yeah, here is the other remaining term that I mentioned. Like, I mean, the original terms are kind of like sine and then the cosine 10x term. So we didn't include those terms in our loss function. So then we get this flat line, I mean, the inference. So which is quite normal, I think. Okay, assume that, like, I mean, yeah, okay, we are adding this loss function, which we don't have a quite confidence on our loss function, the equation, which is partial information, but we know that like our data, let's say this 32-point data, which is coming from like sinusoidal, like the true solution, the ultimate true solution, and we believe the obtained data are more, I mean the truth. Okay, we weighted 100 times more those data, but still we constrain a wrong, I mean, missing, like not wrong, but incomplete like equation. So even if we do that way, so we weighted like the points more, the true data more, but the equation itself just like just 1% of the true data, still the PIN doesn't able to recover the correct equation. So that's the challenge for the PIN. Like, I mean, so if to be able to, I mean, in my belief, like to be able to use the PIN, like we should use the, I mean, like we should regularize the equation according to the correct physics. Of course, like this example is exaggeration. Maybe in real life example, I mean, the observation, the true data, and the belief is not so exaggerated. I mean, this is just a cook-up example to illustrate like my point. Like, I mean, why I kind of like try to develop like this physics guided machine learning or physics guided neural network or this inductive bias type of approach. So in this inductive bias approach or physics guided machine learning approach, so what we try to say, okay, I have a kind of like I mean, the YC here, it's referred the missing solution. Like, I mean, like the solution coming from the missing physics. So, which is just the curve. Like, I mean, just the exponential function. So, it is the solution of the incomplete system. So, I can train a neural network. Okay, I can train a neural network using a regular standard plain vanilla machine learning approach. But while I am training like my approach, like my machine learning like approach by using the same 32 data points. So instead of like regularizing the loss, so I am providing the coarse grain solution or incomplete solution as an inductive bias, like when we are training. So I will come to more details, like I mean in a future slides, but this is just a motivation, like I mean a motivating slide for me, like why I came to think of this inductive bias approaches. So, and then in our group we call it like PGML, physics guided machine learning, and then it is a way of using incomplete physics information or any data, any information, any bias, any laws, any physical laws, or like approximation theory, depending on the problem, whatever information that we have, like in turbulence law, we have energy spectrums or power laws or whatever. So any type of information that we may know, I mean, in terms of the physics, okay, let's embed through the internal like layers of the neural networks to kind of like make an inductive bias in inference instead of adding them as a loss function, because they might be not, I mean, the data and then those things might not be compatible or may not be reflective. So it is just another way of like making a scientific machine learning engines or approaches. So I mean, these are the two kind of like plots. So one of them is like, let's say, physics guided machine learning, and then the other one is PIN. Under the situation of we only know this missing physics information as an equation. Like that's the ultimate knowledge that we may get. So assume that we are not able to think other like cosine and sine terms. I mean, assume that we believe that this is our equation. And then, but we also have a true data coming, like true data coming. Under this situation, there is a benefit of like using the physics guided machine learning against the PIN. Of course, there is a way of like combining. So these are not two competing approaches. I mean, actually they are complementing approaches. So I mean, you can always use like PIN idea within the physics guided machine learning, and then to make it even better, like I mean, by finding the approach, like sweet spot between like the weighting numbers and so on and so forth. So that's kind of the generic idea. But what is the good thing about PIN? So or bad thing about the PGML? So if instead of 32 grid point, if I reduce the available number of true data to 16. So like less data points, so more sparse data, like I mean inference from more sparser data, available data. So then the PGML fails. I mean the regular machine learning fails, the PGML fails. Okay, but the PIN, like by using like 16 data points, like still at least like capture the trend. Okay, so then there is a kind of trade-off, like where to use PIN, when to use like PGML. So I mean, if we have like sparse data, we can kind of more like we can use like I mean the PIN or loss function regularization. I mean, when we have like data like PGML seems better, and then these can be combined. So I mean that those initial slides, I mean, I just wanted to add like to illustrate in the beginning of my talk, like where this PGML idea is fitting into like PIN, like I mean the differentiation between like these two ideologies, like one of them more tailored for like sparse data regimes. I mean, and then assume that like you know the true physics, the equations and so on and so forth. The other one is tailored like I mean. Like you don't know the equation itself, you may not know the full equation itself, so but you may have some sort of like knowledge or information or inductive bias, like any additional piece of information that you can add to your engine, to your learning engine, to make it like more certain, less uncertain, and so on and so forth. So with that one, so this was just the parentheses, like in the beginning to my talk. So I just edit those slides when I was kind of listening to Tobias' paper. So it was just a last minute modification to my talk, just to make a context, like what is spin, and then what, I mean, I thought that like it could be like really good after Tobias' like presentation, like to add those slides. It was like, I mean, we generated those things many times ago. So what we have been doing so far? So, and I try to develop, like, I mean, this hybrid idea or hybrid models, like in two contexts. Like one is largely simulation context, and then the other one is like, let's say, projection-based modeling or reduced order modeling context. So in both of them, so due to the like computational resources, we have a cutoff scale. So I mean, all resolution or grid has a certain capacity, so we cut in certain scale, and then we would like to model the truncated scales, truncated like modes or truncated like effects into the model, and then we make best out of, like, I mean, if the model model that we generate in this blue region is a good model, and then our ultimate solver or ultimate solution is going to be more physical, more representative, more, I mean, so that's kind of like the big framework, like, I mean, the closure modeling, I mean, I call the closure modeling framework or residual modeling framework. And then the role here, I mean, of course, the ultimate, I mean, the gain, like the ultimate gain with all this cutoff, because of like we cannot afford like the direct numerical, we cannot afford to simulate all the scales, and so we have to cut it off somewhere, and then depending on our budget. So I mean, it's called coarse graining, reduced or simplified model, so, like surrogate, depending on like how coarse we would like to go. Like what is our quantity of interest, what is our target coarsening? Like, I mean, largely simulation is not so coarse, I mean, compared to, I mean, the direct numerical simulation. But if we do like a Galerkin projection system with just 10 modes, 20 modes, like to model like billions of grids, like systems, I mean, it is really coarse. Like, I mean, so there is a trade-off, like how coarse like we go, like what type of like coarsening we are doing. But the fundamental principles are similar. So there is always like a need to kind of incorporate the effects of the truncated scales into the system, and then I try to think like how we can kind of add those information. So the first part of the talk, I will focus on the LES part, like largely the simulation part, and then just to put a context, like, I mean, what it is, like, I mean, probably many of you may know, I mean, already, but for, I mean, for the sake of completeness, so, I mean, we may have a partial differential equation arbitrary. So here I just put like, I mean, a simple one, but it could be like, I mean, this is a generic form of any Navier-Stokes equation, or any type of nonlinear partial differential equation can be fit in this form. So we kind of apply a filter. This could be think of a coarsening operator or any low-pass filter. I mean, in any sort of like, I mean, operator to our governing equation, governing system. And then because of the nonlinearity because of the nonlinearity available in this F, okay, and then there will be a closure term due to the like these nonlinear interactions. So and then often, like, I mean, the closure problem comes in the form of how we are going to approximate filtered quantity, like unfiltered quantities from the filtered quantity. So that it becomes a kind of like approximation problem, and then like there are kind of like approaches, like more iteration-based approaches. So one of them is approximate convolution, and then like the original variable, like, I mean, it has been developed in the image processing community. Like, I mean, this was like before all this, like, I mean, the neural network machine learning era. I mean, so we can kind of use one-step iteration. I mean, simple like Richardson type of iteration, fixed point type of iteration to approximate original data, original variable from the filtered variable. So it is kind of an inverse filtering approach. So and it has been transformed to the fluid dynamics community because, like, I mean, at the end of the day, so we have a filtered solution. Like, I mean, when we make a coarse-grained like simulation or larger simulation, so it is kind of a filtered solution. So how we can kind of add like how we get like unfiltered solution from the filtered solution. So then I have been doing like this approximation, evaluating like different algorithms during my PhD. So once I start here in Oklahoma State, I thought that, like, I mean, yeah, okay, but I mean, this process can be also done by machine learning, by neural networks. So I mean, we can train based on data, and then we can see, like, I mean, what is the quality of the approximation, like, I mean, from the coarse grain simulation, I mean, to the like upscale like quantity, like, I mean, so then we, in our early studies, so we see the potential. Yeah, okay, so the machine learning neural networks can be really a good fit for this problem, this closure problem. And then we did some like test for noisy data, for for filtered data, a certain level of filtering, and then we see the potential. But there was, like, I mean, the question, okay, these are all data-based kind of inference techniques for turbulent flow. So, and I mean, do we really get, like, I mean, a good map, a good kind of supervised training, like, out of all these like technologies, like neural network developments and technologies? So the first question came to us, like, okay, if I train, like, I mean, a low Reynolds number, I mean, based on a low Reynolds number data, is it going to be good when I test for high Reynolds number data? So I mean, is it kind of transferable, like this learning can be? So we did some test analysis. So like some of these kind of like results has been already published in different avenues, different journals. So my story here is like, I mean, there are like, I mean, good things, benefits, but I mean, there is always a question of like how I mean, what is the role, or how we can improve like these tools, like this machine learning, these engines, like these learned engines. So I mean, instead of like exploring further in 3D, so I downscale like the problem in 2D to investigate further on the engine, like the machine learning component of the, I mean, instead of like 3D turbulent flow physics, so I downscale like the problem into two-dimensional kind of setting, two-dimensional like Kriegman turbulent setting, and then to identify what type of inference algorithm, learning algorithm could be useful. So I mean, the outcome of these 2D studies can be also applicable in the ideology sense to the 3D turbulence as well. So, and then let me illustrate, like, I mean, the process. So we have a nonlinear equation, like 2D Navier-Stokes in the vortice stream function formulation, and then we have a filtered equation, and then we have a term to approximate due to the like nonlinearity, and then we have a map, like a trained network. So like I have a resolved field as an input, and then I would like to approximate the closure, the contribution of this small scales, the blue part of the earlier figure, like the model part of the earlier figure. So, and then here is some sort of approach, like some sort of idea. Like, I mean, I can easily map like the available data, like the vorticity and stream function in this case, and then I can map this data into a closure term. So, I mean, I can find like the best neural network architecture, or I can do like an optimization to find, like, I mean, to search the best neural network, like parameters, hyperparameter tuning and everything. So this is a way to go, like one way to go. But another way to go is the inductive bias approach. So, I mean, you can still use the plain vanilla approach, like a simple feed-forward neural network or whatever. But instead of just from the available output, like from available input to desired output, okay, you may have additional features. You may have additional like information like strain rate, vorticity gradient. In future, I will show some other things. So some additional information about, and then these additional information actually available in your solver. So whenever we kind of write an Navier-Stokes solver, all these components on the filtered layer, like vorticity gradient or strain rate tensor or other invariants, are available in our solver. So we don't have to recalculate them. Like we already calculate them in our subroutines. So, and then we can feed them, and then this additional induction, like this additional piece of information, we see that, like, I mean, improves the inference quality. So this was one of our first kind of exploration. Like, I mean, that was our enlightening moment. Like, okay, like, I mean, there is a room for this inductive bias in this inference tool. So, and then we kind of generalize it in our following studies. So, I mean, not just like, I mean, the available data, I mean, in our routine. So we have lots of like simplified models, like, I mean, asymptotic laws, like, I mean, scaling laws and other things. So we can embed into our engine. So one way to think, I mean, later, like this approach has been popularized like in a few months ago from like Meta, I mean, Meta AI, Facebook. And then they introduced a new package like physics-informed, I mean, or physics-guided like machine learning package like called Thesis. So I mean, it's pretty much like, I mean, it shares like same idea. So I mean, we have a network, and then we have knowledge, prior knowledge, and then we are adding those prior knowledge into our system, like not just the loss function modification, but also like, I mean, internal layers. So I mean, these two approaches, I mean, share similar ideologies like in the background. So and to illustrate or to solidify like the idea further, what type of prior information we may have. So let's assume that like I would like to make an inference for a flat plate, like very simple like homework problem in CFD, in computational fluid dynamics. So, and in our fluid dynamics books, we have like, I mean, this power law. Like, and we know that like, I mean, this power law is a fairly accurate representation for the boundary layer profile. Okay, this information can be considered as a prior information. So what to do with it? So here I can get a data like using any CFD algorithm. I can generate some synthetic data, and then I can sample some training data. Okay, and then I can train a neural network, and then I'm looking this white dashed line as a prediction, like, I mean, to see that like what is going to be the velocity profile. So, and then here is kind of the difference between like the regular training using the same data and then the physics-guided machine learning. So the difference between ML, the top row, and the bottom row, the physics-guided machine learning, in the same neural network architecture, same mapping, everything same number of neural net. I mean, in the physics-guided machine learning, we embedded this power law when we train, which is a prior information, like, I mean. So as we see here, so I mean, this 5%, 10%, and 30% here in the graph means that, like, I mean, I am sampling like from all synthetic data, I am sampling 5% of the data points, 10% of the data points, 30% of the data points. So I mean, it is just increasing the size of the data, training data. So if we have like, I mean, like more and more data, even for machine learning, like the regular machine learning, I can get better and better like result, which is normal. I mean, expected, like, I mean, but the PGML, the physics-guided machine learning, even if we have like less data, I mean, since I just simply use this prior information, this power law, simple asymptotic theory, I mean, it still forced the neural network to get this profile, the boundary layer profile. So when we see that moment, so we become like, I mean, really happy. Yeah, okay, this inductive bias really works. So I mean, I zoom here, like in the other plot. So I zoom here, like the boundary layer, like, I mean, close to the boundary layer. In the traditional machine learning, as we see, like there is not enough data for the engine, there is not enough data for the machine learning engine to provide. There is a profile, like there is a kind of traditional like boundary layer profile. So the algorithm doesn't know that one, because like there is only very sparse data in training. But in the physics-guided machine learning, it captures like this profile. Although we don't have the data, like but we infer, we kind of induct a kind of information saying the training algorithm, you should respect like certain law, certain boundary layer law, like by putting like this power law. That type of ideology. So we can generalize these things to in many different kind of settings. So one way to think, another way to think. So let's say like this is a traditional like example in aerodynamics. So like the CL/CD curves or angle of attack, like the lift coefficient. So I may have like different shape and then different angle of attack. I can train something like an engine to kind of make the aerodynamic characteristics. So and then the colored part is again like the same business. So like you train many neural networks, and then the standard deviation of all possible neural networks. So is highlighted in the colored like shaded area. Like so, and then the mean of them is the line of all these like machine learning like predictions. So when we train like all these things from a CFD or from an experimental data, so we can generate this type of graphs, okay. But on the other hand, like we have XFOIL, like a panel method, a simplified method, so a low-grained like numerical procedure, which is not costly as CFD or which is not costly as experiments. Okay, so but it can be click and see, like the answer could be. So when we incorporate like these panel methods in our training as a kind of inductive bias, okay, we see that like we can reduce the uncertainty of the prediction, and then we can increase the trustworthiness of the machine learning. So same structure, same machine learning, same type of architecture will be, improved. Like by inductive bias. So I can increase the number of examples with the benefit of like this inductive bias. So and this I just wanted to talk a little bit on philosophically why I think that like this is something working, like or why it might kind of it makes sense to me, at least. So this can be maybe understood in the convolutional neural network like setting. So so we like once, several years ago, like my colleagues, my friend, like Adil, Rashid, and his students, like in Norway, like Norwegian Science and Technology University, and they have video, like recorded video, and then they make like lots of like images from the video, and then they use like this you only look once algorithm. And then it's a huge neural network. 100 layers, like like lots of skip connections and many things like detection layers. So it has been pre-trained, and then like millions of images has been included. Okay, and then you give like this kind of the video snapshots, and then it was, the goal was trying to detect like the number of fishes, like like that, and then this was just an application project. So then to illustrate like the idea, like my goal is not to introduce like this as an example. So my point here, we take this YOLO algorithm, the pre-trained, like highly sophisticated like CNN algorithm, like and then we look at this detection, like how this detection actually happens. So I really would like you all like to make a journey, like when we have an input image. So that input image goes all the layers, like one by all the, this input image, like data, transfer all these things, and then at the end of the day, and then it says that, okay, you have like cat, dog, or whatever, like like fish, and so on and so forth. So now that YOLO algorithm has been trained, and then this is an image, a new image, which has not been used in YOLO algorithm. This is one of the Adil's painting, his own like painting, oil painting image. So we give this image to the algorithm, to the YOLO algorithm, and then we track like in a GIF. Like I mean, we stack all the data, transferring like the neural network towards to the ends. Like I mean, maybe the layer 80 and the layer 96. So we stack all this data, and then here is the following GIF image is how data goes. Like I mean, to be able to detect, like I mean, what is there? Like we have like tree, we have house, we have kind of like I mean, it didn't detect like the mountains, maybe because of the contrast and so on and so forth. But at the end of the day, when we give like this image, it predicts like this, like that YOLO algorithm predicts, like gives us like tree, house, and then like that one. But let's see like how this prediction happens. Like I mean, here is the GIF image, because like that algorithm has been trained with cats and dogs and snakes and castles and cars, and like there are many images. So I mean, the data goes like in many layers, and then we see all these things, and then when we see like that thing, so we think that okay, like this inductive bias. So when the data goes through the layers, so what we are saying with this inductive bias, okay, we are kind of like saying that, oh, okay, like don't go this way, don't go. So I mean, there is a boundary layer, like you should respect like certain laws. So I mean, we try to constrain like every layers when we are training the data. So it helps reducing the uncertainty. It helps like I mean the training time. So we train like the same accuracy way ahead of the time. Like I mean, it reduces like it accelerates the training time, and then there are like additional benefit of this inductive bias. Like I mean, so that was our like motivation. So and this is one part of the concept. So and another part is like when we do our early simulations, so I mean, let's say a CNN prediction for a closure term, like when we generate a convolutional neural network architecture, I mean, for predicting disclosure content or whatever. So, I mean, the by default, like by definition, like I mean, it is translation invariant and Galilean invariant, like these tools, like this CNN. So, but they are not rotational invariant. I mean, so if we kind of like I mean just to illustrate like this thing. So I mean, let's assume that we have two Gaussian vortices. I mean, put it in a field. So and then they interact. Okay, so I mean, like they evolve. Like and then we collect like 500 snapshots. And then we train a neural network, and then we see like what is going on. So I mean, so here is the true in the middle. I have the picture for the true closure. I mean, at a certain time, and then the next picture is the model, like the machine learning prediction. I mean, which is okay, fair, because like I just use this initial condition. And then I evolve, and then I train, and then I test. So same data training, and then same data for testing, like at a particular time. So which is not surprise. Like I mean, it is okay. Like I mean, but assume that like I mean, now I have a trained model. I already trained my model. I simply change my initial condition for my testing. So instead of like a side by side like vortices, now I have like top and bottom. Like I mean, I just rotate it. I mean, so as a human intelligence, so I can really think that like my closure, whatever time it is, they might be rotated. So I mean, the true closure I would expect like this one. Like without any training, without any kind of like with human intelligence, anyone like any of us can easily like rotate this picture. But for a typical CNN, for a trained CNN, it is not that simple task. So I mean, this is the same trained algorithm, same CNN algorithm output. it clearly demonstrates it is not rotational invariant like the traditional CNN. Whenever we train, so and imagine that like in turbulence model prediction, in turbulence flow prediction, so there are a bunch of vortices interacting each other, and then in each time we are not, if we are not respecting this rotational invariance, like all this data, whatever we learn, it becomes like mixed. I mean, so what we see, like I mean, like there are like I mean different ways of like respecting like this rotational invariance. So one of them has been promoted from like Netherlands group, like Maxwell group. So I mean rotational equivalence CNN. So I mean we can do similar things by like data augmentation approaches as well in a certain level too. So what we do with if we do like this rotational invariance CNN, so with additional channels, so by rotating like I mean depending on our user, like if I would like to respect like at every 90 degree, at every 45 degree, whatever. So I mean, even if I train that condition, the upper layer condition, and then if I test with rotational one, it still works. So I mean that way, so it tells us like I mean like whenever we kind of train an engine for a particular application, in particular like fluid dynamics application, we should respect like the physics, the rotational invariance, the closures, the kind of physical load as much as possible, like to be able to. So this is just one step like forward in our in designing like or prediction or prediction engine, predictive engine. So I mean, in terms of more quantitative, like I mean the fluid application. So let's say we have like data from like Reynolds number like 16,000, and then we have like DSM is like dynamic Samogorensky model, like the traditional larger simulation model, and then the frame invariance CNN is the one like I mean which respects I mean the rotational invariance. So as you see that like the true solution, which is filtered DNS, FDNS, I mean the trained model, the machine learning based closures are kind of like they are more close to filtered DNS. So that's kind of one positive fact for this kind of data driven based closure modeling approaches. So but what if we test with higher Reynolds number, like which is not included in the training? So I mean still like I mean the like the frame invariance or the tails of the density function, like I mean like probability density function, as you see that like I mean it's more close to I mean way better than the dynamic Samogorensky. So if we put like I mean the energy spectrum, we can see that like I mean it captures like I mean the inertial range. So there are benefits of doing like this approaches like in the statistics of turbulence. And then like I mean I can I don't have much time to kind of go details, but the message I would like to show. So I mean here like in the prediction in this particular case, like in turbulent flow case, so if I use this, if I respect the physics, the frame invariant, in this case, let's say the rotational invariance, the vortex interactions, and then even if I run like beyond the training time, even if I run further in time, it is not blowing up. So I'm not tuning the algorithm. I am not clipping the algorithm. I am not kind of adding in artificial dissipation to smooth things out. So, I mean, I just run further to model, further in time to model. It still runs, and then it still don't, I mean, it is not blowing up, and then it provides like a prediction and inference, like even for higher Reynolds number. But for a regular CNN, for, I mean, if we don't respect like this certain like properties, after a certain time, like in the early time, everything might be good. Like if we are in early stage of the turbulence or early stage of the interactions, I mean, it may be okay, but later in time it blows up. So the green curve in this upper figure in the left side, I mean, the green disappear in the later time because the code blows up. Like I mean, it is I mean, the error accumulated due to the this rotational invariance accumulates in time, and then it's not kind of continuing. But if we respect physics, I mean, or if we respect certain conditions in our inference tools, in our predictive tools, it continues longer time, and then there is additional benefit of doing this engine. So this is one aspect. So I mean, another another few slides, maybe 2 more slides, I may continue here. I mean, this all so far everything was kind of a kind of supervised, I mean, regression type of approaches. So how we can kind of think in terms of a classification way. I mean, how we can utilize these engines, this machine learning, or the power of, I mean, this neural network in fluid dynamics, in closure problem, in particular in this case. So in terms of classification, so in that approach, so I mean, we can develop a kind of a hypothesis. So I mean, this is a very plain vanilla version of the kind of a reinforcement learning type of approach. I mean, I consider it that way. So I mean, we have structural models, we have functional models like eddy viscosity based models, we have Bardina models or scale similarity models or approximate convolution models, different type of models. I mean, in any CFD solver, in any fluid dynamics solver, we have options of turbulence models. So based on certain kind of criteria or based on certain hypotheses, okay, I can let the algorithm, the machine learning algorithm, instead of making a data-driven closure, it based on the space-time correlation of the space-time evaluation of the flow, it can select okay, now I am going to use this particular algorithm for this particular condition. I'm going to use this particular algorithm for this particular condition. So we can kind of let the let's say open form or any software to decide automatically which type of models they are going to use, or it's going to use for a particular flow application. So and then we see that I mean a simple example, dynamic Simogorensky model in one side, approximately convolution model on the other side. And then if we train a machine learning and then let them mix them depending on the condition, we see that it is giving better approach, better than the dynamic Simogorensky itself, better than the approximately convolution itself. So I mean, it is, I mean, and then it is safe. So we are not kind of using any arbitrary a model, any data-driven model. It is safe because we are using one of them, one of the theoretically rooted model. But the AI, the role of AI is choosing them, what to choose, which model to choose at a particular condition. So that's kind of another way to go, I mean, the machine learning for turbulence or for turbulence closure. So of course, this is a model part. So what if we switch these ideas in numerics? So there are central schemes, there are upwind based schemes, I mean, some of them adds artificial dissipation, some of them don't add artificial dissipation. Some places we may need artificial dissipation, some places of the flow field we may not need artificial dissipation. How an AI can mix them, I mean, so I mean, this is another way of kind of using I mean the machine learning, I mean, and then we see quite a bit of good and I mean decent results when we mix these ideas, when we use numerics in deciding which type of numerics needed in which part of the solver. So I think I will stop here. The same equivalent versions or equivalent ideas that has been done in Elias on the similar format. So we apply them in POD, proper orthogonal or Galerkin reduced order model, how to kind of develop physics guided machine learning for Galerkin projection. So in the second part of my talk, I mean, I have those examples, but the conclusions and the benefits pretty similar. So I think I would be happy to take the questions for the first part, and then let's I think let's start for questions. Like, I mean, I think it's time to wrap things up.
It's all right, Professor. We can extend the seminar a little bit longer. But yeah, do we have any questions for the first part from the audience? But Professor, how many slides do you have for the second part?
I mean, like I was kind of making a case that I think a few, maybe 5-10. Like I can make it. I mean, I can continue 5-10 more minutes if you wish.
Yeah.
Okay. So the reduced order model, like the projection-based reduced order model, I mean, it is a model decomposition. So like from the data, we approximate some sort of basis function, and then we project like our system to this basis function, and then convert partial differential equations into ordinary differential equations. So it's a classical classical way of doing Galerkin projection. I mean, Galerkin projection-based reduced order model, or we call it GROM. Okay. So, and then, but at the end of the day, like once we do like those type of things, so our ordinary differential equation becomes R cube. Like the scale of the Galerkin projection systems becomes like the number of mode. The R is the number of mode, and then it scales with the R cube because of the nonlinear interaction. Like, I mean, in Navier-Stokes, we have this quadratic nonlinearity. Because of this quadratic nonlinearity, it becomes R cube. Like, so, I mean, if our system, like, let's say we have 3-dimensional system, like, and then in each dimension I have 100 grid points, so I have 1,000, 100, I have 1 million grid points. So I have a 1 million grid point system, and then I can reduce 1 million grid point system into 10 modes. Like if my R is 10 modes, the most sophisticated or most energized, like 10 modes, or most dominant, most important 10 modes. So my system, my R will be 10. So 1 million degree of freedom becomes 10 degree of freedom, which is a significant like projection, which is a significant reduction. But to run these systems, my algorithm is 10 cube. So I mean, because of all these like summations involved in the right hand side, so the computational cost becomes like 10 cube, which is 1,000, which is like practically it becomes a system of 1,000 degree. I mean, operations, like which is still like 1,000, still like significantly less than, I mean, 1 million. Then it becomes like a great research topic for many people, many researchers, like this projection. I mean, it was kind of one of the main like reduced order modeling approach in the community. So what we are doing here, like pretty much, I mean, so we have a full trajectory, and then we kind of like project that trajectory to a layer, a linear layer, and then this is a projected trajectory. And then the error between them is our projection error. I cannot do much things for this projection error, like in the first phase, because it comes from the reality of like the projection itself. So I'm projecting onto a linear layer. I mean, of course, I don't want to project into linear layer. I can use like autoencoder and so on and so forth, nonlinear reduction techniques. But let's assume that I'm using a linear one now, and then I project into a linear, and then I accept that error, which is called like projection error. But when I evolve my dynamical systems on my projected layer, on my layer, I mean, because of the interaction, because of the nonlinear interaction in my system, because of the truncation, I also get wrong trajectory. So I mean, the difference between them is called, let's say, closure error. I mean, the closure error. So what we do in the first phase, we split the errors, the closure and projection error, and then we use certain techniques to minimize this closure error. For example, PGML, the physics-guided machine learning. I can incorporate like the physics-guided machine learning ideas or ideology to minimize this closure error. And then I can use like nonlinear, like autoencoders or variational autoencoders to kind of minimize this projection error. And then for a particular system, like 2D Navier-Stokes like system, so let me just go and finish this one. I think I may skip this one too, just to the point. So I have a I have a system which is full order model, like the complexity of 256 square grid. This is the dimension of the system. So the Galerkin ROM, the standard Galerkin ROM, if I reduce this R, the number of modes 20, the complexity becomes like 20 cube. 20 cube is a huge number, like it's almost close to like the complexity of the full order system. So, I mean, my goal is not to reduce like 20 cube system. So my goal to be able to get something really accurate by using only 6 modes. So the complexity of my system is going to be 6 cube, which is going to be significantly less than the 256 square. So here is the PGML. I mean, plus autoencoder means that like I reduce the closure error and I reduce the projection error through the help of machine learning somehow. But if I don't do it, here is the plain vanilla reduced order model on the complexity of the 6, like the 6 cube. So there is a significant benefit of combining the ideas like from the data science or machine learning within the like reduced order modeling community or projection based modeling community. So that's, I think, my last slide. Like I just wanted to give this message. Like, I mean, like by identifying the source of the error and then finding a correct machine learning approach to compensate the error in a certain kind of component. So there is a way to improve the tools, the predictive tools, the engines, like, I mean, even with desired, like, I mean, accelerating the solvers, like still we can get like pretty accurate result with the complexity of 6. I mean, that's kind of, I think, my kind of final slide. And then it is still in the early times. So all these like physics informed AI, I mean, according to the like these agencies like Gartner, McKinsey. So we are, I think, like in the beginning of a big leap. So there are lots of ways. Many groups are trying to find the best way of like fusing different, like, I mean, physics and data-driven approach. So I'm particularly looking for fluid dynamics applications. So I try to reflect my my group's research, like part of my group's research here in an hour or something like that. And I appreciate your time, and happy to take any questions if you may have.
Thank you, Professor. Yeah. Do we have any question from the audience?
Yeah. Hello. Yeah, I'm curious about that FICNN, the rotational equivalent neural net. So how are you using Max Wheeling's rotational equivalent neural net like CNN, or are you doing the data augmentation?
I mean, that particular figure was from this the original approach that has been provided by him. The one I presented here. But we also test, like, we also have like figures, like if we do, like, I mean, data augmented way. So I mean, we have original kind of snapshots, and then I can rotate, like, I mean, my original data sets. I can regenerate like different sets of like rotated versions of the same data sets, and then I can train based on extended data sets, and then I can get improved results pretty much. Like, I mean, of course, if we use the original approach, because it is already embedded in weighting. So I mean,
right.
Already embedded in the code, like, I mean, all these weights. So it is more efficient if we use the original idea. I mean, original frame invariant, like, I mean, the framework proposed by him.
I see. But in the augmented, I mean, data augmentation approach, you see better stability in the long-term prediction, is that, or better prediction of the distribution of the turbulence data?
I mean, I said better. I mean, I didn't compare like data augmented version, like, I mean, data augmented version versus the weight, like the channeling version. So you add external channel within your CNN data. So instead of, like, let's say, one channel, you define a parameter which is, let's say, 8, which makes like every 45 degree, and then you kind of like get 8 different weights. Like, I mean, you increase the number of parameters in the original, like, I mean, CNN, I mean, like the architecture. I mean, I compare, I'm saying like it is better if you don't do like this frame invariant idea at all. So I'm not comparing like the data augmented version, like, I mean, or frame invariant version. I mean, they're I mean, in this particular, because this example is like relatively simple example. Both of them works, like whether you do it in data augmented version, because at the end of the day, like my test setup is 2 Gaussian vortices. I just rotated. So if I use just 2 channel, I mean, if I just use like, I mean, 4 channel or 90 degree rotation, I mean, data augmentation will provide me like accurate result, like, I mean, or frame invariant. So this is a just cookup problem, just to illustrate that, like, respecting like any sort of physics will help to develop a better engine. So that was the idea behind that figure, that study.
Yeah, I understand. Yeah, but I think that's a great work. You show this kind of the rotational invariant improve the prediction results. So do you have, is this work already published? Because I want to try to
that one was part of a paper, like this plot was part of a paper that Suraj Power published, like one of my PhD student published that work. It's available on Physics D, like I think the title was Frame Invariant Closure Modeling for Kriegman Turbulence or something like that. I don't recall that.
Yeah,
title,
if you don't mind, can I send you an email? I mean,
sure,
I'm here from Lehigh University. Yeah, so then because I'm really interested in this topic, and we also have some development along this line. Okay. Yeah. Thanks a lot. Yeah, great talk. Yeah, it's great meeting you.
Do you have any other questions? All right, thank you, Professor, for your presentation. And Professor George Kanedakis cannot make it, but we're recording this seminar and we're uploading the recording to YouTube, and he'll watch it later, and maybe he'll contact you later. So yeah, thank you for your presentation today. And so this is it for our Cron seminar this week. I hope everyone has good Friday and weekend. See you next week. Bye.
Thank you.
No problem.